Only a few sections to go as we get all the way up to 15.5, and that'll do it. So what I started last time, same section 15.2, after seeing how Legendre polynomials are orthogonal, I started an example where we had a Laplace equation, potential, and I started the process of solving it using separation of variables after converting to spherical coordinates. And this is where I left off last time, that we already solved, because we have our spherical coordinate variables, r, phi, and theta, and we get an ODE for each variable, and the ODE for phi had already been solved because your solution has to be 2 pi periodic in phi. So we still have the ODEs for r and theta that we have here. So that's where I stopped last time. So now we're going to continue working with these two. Okay. So we have a requirement that for theta, that has to be non-singular. This is our domain for theta. Keep in mind, we're using the physicist convention for spherical coordinates. So theta is the variable corresponding to what's called the angle of inclination. That goes from 0 to pi, whereas theta is the angle for the azimuth that goes from 0 to phi. Phi is the angle for the azimuth that goes from 0 to 2 pi. Okay, so what happens is with theta going from 0 to pi, then we make a change of variable t equals cosine theta. So t is going to range from -1 to 1. So we require that the our solution is non-singular on this interval in t. So we're going to use this change of variable to obtain a new ODE from this one in t. Now, I'm not going to go through all the messy calculus. It's basically an extensive chain rule exercise. But you need to write derivatives with respect to theta in terms of derivatives with respect to t. What ends up happening is this ODE in t is what pops out. Now, we're going to focus on the case where m is equal to 0. So this term is gone. And the coefficients that we have 1 minus t squared here, and minus 2t here. This is, with m equals 0, this is Legendre's equation. So in that case, we know what the solutions are. That they are so p of t, the solution in t, must be a Legendre polynomial. And notice that both of these ODEs that we got from separation of variables, we have what's called a separation constant. And at the beginning, when you're performing separation of variables, the separation constant is unknown. It ends up being determined by whatever boundary conditions you have. In this case, for Legendre's equation, the solutions over Legendre polynomials provided that lambda is equal to this product of consecutive integers. So L equals L plus 1. I'll make a note of that here. For some reason, my text down here where I type gotten really small. It does that now and then. And I can never remember exactly how to fix it. Okay, I think I'll just have to deal with it this time. Maybe I'll fix that accidentally. All right, so to make clear that L here is an integer, so then the solution will be the Legendre polynomial of degree L. And that is needed to make sure that the boundary conditions are satisfied. Because what we saw some time ago when we considered Legendre's equation and applied Frobenius' method to try to solve it, what we found is that if a solution was allowed to be an infinite series, then it would diverge at plus or minus 1. And we can't have that here. It's required to be non-singular. The only way to do that is to make sure that lambda is such that the power series solution for Frobenius' method terminates after a finite number of terms. And again, this is a rehash of something I presented some time ago. It's a Legendre polynomials that result from getting that kind of solution. So it's this equation that determines the valid values of lambda, L plus 1. So we take that and we substitute that into this ODE, the only one we haven't solved yet, for lambda. So this is our ODE in lambda now. So we can try tackling this with Frobenius' method. And what happens when you do, again, I won't go through all the details, it's the same mechanics that you see in the various examples or homework problems. The indicial equation that you get from Frobenius' method is s times s plus 1 equals L times L plus 1. So one obvious solution to this would be this s equal to L. But the other possibility is that if s is equal to minus L minus 1, that also works. So basically what you have here, if you take this L times L plus 1 and move it to the left side, have everything set equals 0, you get a quadratic equation in S. So you can solve it using quadratic formula. And these are the two solutions that you get. So when your solution has what's called radial symmetry, and so in other words, the solution does not depend on the angle phi, which is what happens when m is equal to 0. Then this is your solution to Laplace's equation. So we're going to stick with that assumption of radial symmetry just to simplify matters. So because what your solution is linear combination of solutions of this ODE times solutions of this ODE for the same value of lambda. So the solution from the equation for theta is Legendre polynomial evaluated at t, but remember t is cosine theta, so that's what we have here. Our solution has to be a function of r and theta. And then the solution of this ODE turns out to be, when you get from Frobenius' method, is a solution little r raised to the L power. And then if you use reduction of order to obtain a second linearly independent solution, you get this one, r to the minus L minus 1. I just something I want to check here. Okay, if I think that's something that might have come up in a one of the homework problems. Okay, well, it is the Legendre equation right here, but the other ODE I was thinking of this one, but this is not exactly the same. So this is an ODE where you get R to the M from Frobenius's method, and then if you use the reduction formula order formula, then R to the minus M is what comes out. But that's similar, but it's not the same ODE. And then those two linearly independent solutions are multiplied by these arbitrary, as yet unknown constants. So your general solution for the m equals 0 case has this form. To figure out what the coefficients must be, we need to use whatever boundary condition we have. So this is the general process when you have Laplace's equation in spherical coordinates, and you assume radial symmetry, so solution only depends on r and theta, not phi. This is your general solution. So these powers of r times Legendre polynomials evaluated at cosine of theta. I will go into an example next, but are there any questions about this process?
Yeah. How did you get s equals negative L minus 1 from the
Okay.
like in the sort of equation?
I think I can. What I was going to do is I can take the initial equation.
Yeah.
Okay. Okay, so what we get here is okay. All right, that's just quadratic formula. But I'm curious as to why it works out so nicely algebraically, because it's, oh, wait, that should be a plus, not a minus. Minus 4ac. Okay, yeah, if it, what's going to happen is we get, we have 4 squared plus 1. Oh, that. Oh, that's perfect square. That is. Okay, yeah, that's a. Okay, 2 plus 1 squared. So then we have. Oh, wait, that's plus or minus. Dang it. Oh, yeah, okay, so you get L plus a half. Plus a, okay, yeah, so then you get, okay. That's fine.
Yeah.
Alright, other questions? Shafts? Oh, ghost or something. People eating more responsibility. Yeah, that's what I always forget, that, well, let's try it. Because when I, let's see. Oh, I have a, touchpad, but maybe I can do this thing. Ah, okay. So for Mac, if I hold the command key down and let's do the touchpad equivalent of roll mouse wheel. Okay, so now I can see what I'm doing. Thanks. Oh, okay. All right. Okay. All right. So now let's consider the specific problem. So the idea is, so we have a neutral conducting sphere, R0 is the radius, and it's placed in a uniform electric field, and E naught is the magnitude of that field. So when you do that, the electrostatic potential, which is the psi, that is the solution to the Laplace equation. So that's the PDE that we've been dealing with. So spherical coordinates. So we use a coordinate system where the center of a conducting sphere serves as the origin. And we're also going to assume that the field is parallel to the z-axis for convenience. I'm not sure. I want to check. At some point I need to go to the section and show a diagram of the situation. Okay, yeah, so this example, sphere in a uniform field. Yeah, so that's what we have here. So this is our conducting sphere. And the field is moving parallel to the z-axis. It's kind of weird to place the z-axis where the x-axis is, but maybe it's a physicist thing, I don't know. Okay. All right. So as before, we have a radial symmetry. You know what? I totally blew it. I've been using the term radial symmetry all this time. That's not true. Radial symmetry is when the solution depends only on R. Axial symmetry, which is what we have here, and in the preceding discussion, is where the solution is independent of phi, but it's still allowed to depend on theta. And I don't think I actually wrote radial symmetry here in the notes. Okay. No, I didn't. Okay, but sorry for the misuse of the term. So I'll just write in this here as opposed to radial symmetry, which depends only on R. Here the solution depends on R and theta. So this is what we have here. It's the same form of a solution. The only thing that changes is that I'm using n as my index variable, just for consistency with the textbook. And we have a range of indices going from 0 to infinity. And really that's what we should have here too, because your solution involves Legendre polynomials, and L is the degree. So your sum is from 0 to infinity in both cases. Okay. So what we're going to do here is use particulars of this problem, try to get a handle on what these coefficients are, an and bn. So, because inserting this conducting sphere into a field has a local effect, that as r goes to infinity, the field is actually not affected by the conducting sphere far away from it. So, so what's happening is the potential is in the z direction. The magnitude is E naught. So at r going to infinity, it should behave like this. But in spherical coordinates, z is equal to r cosine theta. Now, we want to express this in terms of Legendre polynomials. Well, keep in mind that P1, a first degree Legendre polynomial, is a P1 of x equals x. So cosine theta can be rewritten as P1 of cosine theta. So the term for n equal 1 has to reduce to this. So if I look at the term for n equal 1, so I have a1 r, and then we'll deal with this term later, but a1 r, and then I have p1 of cosine theta, but because it's p1, that's just cosine theta. So I'm going to elaborate here. So to fit the term a1 r cosine, or p1 cosine theta. Right, so in other words, we're matching this to this, but they're identical except for the constants in front. So a1 is equal to minus e naught. Also, because we only have p1 here, we don't have any other terms going other Legendre polynomials. That means that all of the other a's have to be 0, at least for n greater than 1. The reason why this condition at infinity does not affect these terms is, note that we have a negative power of r. As r is going to infinity, these terms would go to 0 anyway. So it doesn't matter what bn is at this point. So so this condition, all it does is it helps us determine the coefficients for the terms that actually go to infinity. So, in other words, the a terms, the an terms for n greater than or equal to 1. Because when n is greater than or equal to 1, this is going to infinity. When n is 0, we have just a0 times 1. So that's not affected by going to infinity either. So of all the terms that go to infinity, this is the only one we have. And that's what dictates what a1 is. And, oh. Something is wrong here. Yeah, that should say an equals 0. Sure how greater than it's not getting back. Okay. Are there any questions up to this point, as far as at least partially determining this? Now we have a neutral conducting sphere. So that means the side is not allowed to have a term of a growth rate 1 over r. So we're not going to have b0. b0 has to be 0. That corresponds to 1 over r term. Now, on the boundary of the sphere, remember, a sphere has a radius r0. So on the sphere, that the potential is constant, we can assume without losing generality that the constant is 0. So mathematically, we're saying that psi of r0 for any theta must be 0. So when we take this solution here, what terms do we have? We have this a0 term, which at this point is unknown. So this term came from the upper boundary condition at infinity. Sorry, just that right there. Sorry, it keeps highlighting what I wanted to highlight. That was determined by with a minus included. That was determined by the boundary condition at infinity. And then, as I mentioned, b0 is 0. We still have the other b terms as yet unknown. And b1 is multiplied by p1, so that's what we have that here. The other b terms were multiplied by these higher degree Legendre polynomials. And then we still have a0. All other a terms have been accounted for. Now, okay. So in order to make sure that this boundary condition is satisfied, for regardless of theta, so since the whole thing must be equal to 0, and we have all of these constants multiplied by Legendre polynomials that are orthogonal, therefore linearly dependent, all the coefficients, this, and this, must all be 0. So a0 is 0. All the higher order b's are 0. And then to make sure that this is 0, that gives me this value for b1. So now, all the coefficients in this solution turned out to be 0, except for a1 and b1. So, so this is what we end up with. So this is the a1 term, this is the b1 term. And keep in mind that p1 of cosine theta is cosine theta. And r cosine theta is equal to z by the formulas for spherical coordinates. So this is our solution. So this constant and this constant all times z. So yes, so the solution ends up being linear in z, which makes sense because that's the direction that the electric field is going in. So that's parallel to the z-axis. So any questions about how the solution was obtained from the general solution? Okay. another example. So you have a thin ring, conducting ring, radius A, carrying a total charge Q, and it's placed symmetrically in the equatorial plane. So the XY plane is spherical coordinates. And I believe I have a picture of this. Okay, yeah, so this is the situation. So this is the ring of radius A, charge Q. And here we have some point in r theta in the three-dimensional space for some angle phi, but we're going to find a solution that is independent of phi. But here are the r theta coordinates. At least this time z is pointing in its usual direction. Okay, so the potential satisfies the Laplace equation. So we have the same general solution as before, but we actually have to strip it down a little bit because go back to the general solution that we have here. It needs to go to 0 as r goes to infinity. We're regularly looking for a solution that satisfies boundary condition on the boundary of a ring, but goes to 0 as r goes to infinity. So these terms, these terms will not apply. We have only these. So we're trying to, in a situation we're trying to solve for electrostatic potential inside a certain sphere, then you would only have these terms. You would exclude these because these would go to infinity at the origin. You don't want that. So for electrostatic potential inside a certain domain, you use these terms. When you're looking for trying to solve for outside a certain domain, use these terms. So basically, you're going to drop the terms that would go to infinity in the domain of interest. All right, so potential has to go to 0 if r goes to infinity. So we only have these terms. So Cn times a to the n, that plays the role of the Bn coefficients that we saw earlier. The reason why it's being written in a slightly different way is a to the n. It's customary when you have a boundary that's at some radius other than 1, to have that radius raised to the nth power as a factor, because it makes things convenient for trying to satisfy boundary conditions. Actually, those of you who took my 417 or 517 class last semester would have seen that, where in solving actually Laplace's equation, we had solving interior and exterior Dirichlet problems, that we would have like r over a to the n or a over r to the n. So it's the same idea. Now, for purposes of solving for coefficients, if we determine the potential another way using Coulomb's law, then this is what we get at z0. E minus z is equal to r cosine theta. So I take this expression for the electrostatic potential, and here with theta equals 0, this is in the xy plane, but the radial variable is set to z. So, alright, so this is what Coulomb's law gives us. But then we write this as a series where we have, because this is the z squared plus a squared raised to the -1/2 power, we can use the generalized binomial theorem, so these generalized binomial coefficients, the exponent of the -1/2 up here. And if I pull a z out in the denominator, so actually I can go ahead and write it that way. Copy this. All right, so I'm going to pull a z out in the denominator. Z, not a. And then this becomes 1 plus a squared over z squared. So writing it this way, because I want to have it as 1 plus something raised to a power. In this case, the power being -1/2. And that's what gives me this expression here. But now when I evaluate what this binomial coefficient is, I get this expression. We've seen this before, where we have these double factorials. A over z raised to the 2s power. But then, if I take r equals z and theta equals 0 and substitute that in here, then this is what I get, just from cosine 0 equal 1. And keep in mind that I have Pn of 1. All the Legendre polynomials are normalized so that Pn of 1 is always equal to 1. That was certainly convenient here. So now all I have to do is determine the coefficient Cn. Oh, that should be a raised to the n power, not a sub n. All I have to do now is compare this series to this one. And that will determine the coefficients Cn. So notice here we only have even negative powers of z. So Cn must be equal to 0 when n is odd. So then I just have to figure out the even coefficients, and I take everything here that's multiplying. So here I have z to the 2s plus 1, but keep in mind I have a factor of z sitting out here that's been pulled out. And then I still have z to the -2s inside. So by equating these two and matching coefficients for even values of n, then this is what I get. So now my solution is complete. So this is how it works in general, where we have a general solution obtained by separation of variables and solving the ODEs involved, and then whatever boundary conditions you have will determine the unknown coefficients in that general solution. And those come about from like various physical considerations. Okay. So I come to the end of these notes. So now we have plenty of time for any questions about them or any homework questions. From the 3 people we still have here.
You look at 14.2.8.
14 to 8. Okay. Okay.
So like in the book, it didn't have x to the m. It just had like a generic function. So I was wondering if that changes anything.
Oh, okay. Oh, you mean like from this? You mean?
Yeah, no, like 2.8. For like the hint, it said expand XM.
Okay.
Because I wasn't sure if like the same expansion would be the same, even though it's not like a function or anything.
Oh, I see. All right. So if we have XVM, then oh, okay. Um, it's so well, yeah, but for this, I mean, yes, so this would be playing the okay. Um, hold on a second. Okay. Yeah, so x to the m would be playing the role of f of x here. But then what you would need are these coefficients, the an. Okay. So for that, okay, so we have, so this would be, I guess, I think this is now, so x being applicable to this function here. Now, whoops. Okay. So then you'd be using this formula to get to coefficients. So, so this is playing a role of the an in that series.
So like in the like 14.47, there's like a 5/a fraction in there. So how would that be replaced? Would it just be x or something else?
Okay, all right, so we need to match this with the series you're looking for. All right, so we have, okay, so that's x. Oh, all right. Okay, so notice here we have interval from 0 to 1. So going back here, yeah, so a would be 1. Okay. And yeah, so rho is x.
Gotcha. And we just solve for the coefficient and then.
Yes. Now, okay, so what we have here is okay. So then we have x. So this would be jm. So new is m. So what's the translation going on here? So notation here. So jm of 0 times x, and then here we have x to the m. So we really have x to the m plus 1 times Bessel function integrated from 0 to 1. Okay.
Why is it xm plus 1?
Oh, because you have this one. This.
Oh, okay, just another okay.
Um, okay. And okay, and since in this case, this integral, you just be able to work that out.
And as for this, okay, so now we go back to a formula for Bessel series coefficients. Okay, something. Um, then there's a matter of value of, as far as those integrals are concerned. Um, so what the integral you're trying to evaluate to get these coefficients is so this, yes, this right here. So x to the n plus 1 Bessel function of the 0 jm times x. So then you would need what I don't recall off the top of my head is the expression that integral worked out. Oh, okay. Well, you do have this on your side though. So what you're trying to integrate is x to the m times times jm evaluated at a multiple of x. So here we have okay. So this is so that's like reversing this. So in this case, n would be m plus 1. And because you just have plain x to a power here, but you have jm evaluated at a constant times x, you have to fudge with the constant factors to make it work out exactly.
Do you use direct substitution, or can we just multiply?
I would recommend the use substitution. Yeah. I was good at paint.
Yeah, I was confused about how to do that one.
Okay. Yeah, I think you're the first one to ask me about it. All right. Okay. I really need other doozies.
14.3 and 7b.
Okay, so, so in other words, you were able to work out A already?
Yeah, I was doing like iteration of parts. And then
Okay.
I forgot how to like prove something. How do you prove something is linearly independent?
Yes, so the idea is, you assume that they are literally dependent, meaning that one of them is a scalar multiple of the other. And then you arrive at a contradiction.
How would it start? Just so like,
What?
how would it start? Like, how would I start working it out? Would I just
Okay, so, yeah, so you just like y0 is equal to c times j0. Now, oh, so then you have, the thing to keep in mind is that, J0 and Y0 are meant to be the two linearly independent solutions of Bessel ODE. And, okay, so this solution that you got turns out to be a scalar multiple of Y0. Okay. I'm trying to think of something in particular about solutions of an ODE, because in that case, therefore, Wronski, another angle, because we're talking about ODE, to show what they're linearly independent, you want the Wronskian to be non-zero. That might help too.
would it like be a good like? Can I just prove that the Wronski is non-zero, or would I have to?
That would work. Yeah, so normally the way you show linear independence is you assume one to multiple the other and get a contradiction. But because of solutions of the ODE, you have this other perspective you can use.
Okay. But I'm like, I know the question before that you do some Wronskian formulas.
Oh, yeah, I
use
did.
that,
Okay.
use that,
Oh, yeah. Yeah, I'll do that then.
Okay.
Oh, I sense you're packing up. That's your last question?
That was it, yeah.
Okay. Well, no, that's fine. That's good to know.
Do you have any, like, is there anything else? Like,
Well, I don't have anything else. We'll see if anyone else has a question. Oh, and apparently not. So, okay.